Relativity of time. This is grade 12 physics. Today's topic is time dilation. Dilation means you make it bigger or you make it wider. For example, if you go to an optometrist, the doctor will make your pupils bigger. So put some medicine into your eyes, and your eyes will dilate so that more light can get in. So the equation to do time dilation is this. This is the equation. I need to explain what delta Tm is and what delta Ts is. Now let's look at the definition. Ts, delta Ts, is the time interval for the observer stationary relative to the sequence of events. And delta Tm is the time interval for the observer moving with a speed v relative to the sequence of events. Let me explain this. You have a person reading a book. This reading a book is what we call event. And there is an observer. The observer is beside you. So you start reading the book, say at a certain time, say at 7 o'clock. So when you start reading, this observer will look at his clock and notice that, oh, you start at 7 o'clock. And you read the book, maybe you finish 5 pages or 10 pages. So when you finish your reading, the observer reads the clock again, and the observer gets the idea how much time it takes for you to read the 5 pages or read the 10 pages. This time is called delta Ts. So delta Ts, look at the definition. Now again, delta Ts is the time interval for the observer stationary. Here, this observer is beside this person who reads a book. So he is stationary. This observer is not moving away from you. He is stationary. That S, you can say that it's stationary. So stationary relative to the sequence of events. What do we mean by sequence of events? Sequence means this. You start reading, that's the beginning of the sequence. When you end reading, it's the end of the sequence. So the event has a beginning and an end. The beginning and end. So that's what it says, sequence of events. Now what is delta Tm? Delta Tm is a time interval for the observer moving with a speed v relative to the sequence of events. Here, relative to the sequence of events. So this observer is not beside the person who reads the book. Here, this person reads the book. That's where the event is. There is another observer. Here, another observer. This observer also has a clock in his hand. Now this observer notice when this person starts reading, and he look at his clock. And he also notes when this person and his reading, and he records the time. So he has the beginning time and the end time, and this interval is called a delta Tm. The subscript m means moving. Now, these two persons are in the same room. You can say they are in an automobile or in a train. So they are in the same place. And this person, this another observer, is in another room, or he is in another car. And there is relative motion. The speed of the relative motion is v. Relative motion, which means either these two persons can move, or this another observer can move. So let's say these two persons moves. So we can imagine they are in a train, and the train moves relative to this person. You can also assume this person is in a train and this train moves. So you can either consider they are moving, but he is not moving. Or you consider this person is moving and they are not moving. So the motion is relative. The relative motion has a speed v. Now, this is the situation. Under this situation, the relation between delta Ts and the relation between delta Tm is given by this equation. This equation, since the velocity is limited, the motion of a train is not too big compared with the speed of light. So this v is between 0 and c. And you look at the equation, if v is less than c, then this fraction is less than 1. 1 minus less than 1 is still less than 1. And you take square root of a number which is less than 1, it is still less than 1. So delta Ts divided by a number which is less than 1, the result will be a number which is more than delta Ts. Therefore, delta Tm is larger than delta Ts. And this is what it says here. Let's look at another understanding of the delta Ts and delta Tm. The time interval between events that occur at the same position in a frame of reference. What does that mean? The time interval between events. The events is the start of the reading and the end of the reading. That's the events. Now, the time interval between events. Let's move the page a little bit. The time interval between events, between the start of the reading and the end of the reading, that occur at the same position. Same position in the reference frame. A reference frame, you can consider this is a room. In this room, this time interval is less than the time interval between the same events at another frame of reference. Now, the events are the same, the beginning of the reading and the end of the reading. But the observer is not he. The observer is another person. He is in another frame of reference. This is one frame of reference. This is another frame of reference. In other words, if your observer is in the same reference frame, and the reading is called this, delta Ts, and if the observer is in another frame of reference. The reading is called delta Tm. You can consider frame of reference two other locations. So they are in one location, in a train, and he is in another location. He is in an automobile, for example. So they are in different locations. The term is called frame of reference. So this is another way of understanding the formula. And you see the next sentence says, one position time is less than two position time. What is one position time? Look, when this person starts reading and when this person ends the reading, he is at the same position. So that's called a one position. The one position time is delta Ts. What is two position time? Now look at here. When this person starts reading, he may be in this position. But this is moving. This is a train. He moves. So when he starts moving, he is here. When he ends reading, the train moves here. So when he ends reading, this person, the person reading the book, is at another position. So you have one position here, another position here. So the beginning position and end position are two different positions as far as he is concerned. So that is what it means, two position time. The two position time is delta Tm. So the delta Tm is larger than delta Ts here. This one position time is less than two position time. So two position time is larger than one position time. That's another way of saying it. And the duration of a process. This is just another way of phrasing. The duration of a process, which means a time interval of the events, okay, as measured by an observer who sees the process begin and end in the same position. Now, this is the situation. This person sees the beginning and the ending at the same position. This time, delta Ts, is called a proper time. There is a name, it's called a proper time, all right? So, see the brackets? The proper time, the time interval between two events, measured by an observer who sees the events occur at one position. So you can call it one position time. Understand? So, the result, this time is larger than this time, is called time dilation. So let me repeat. The delta Tm is larger than delta Ts. This result from our equation, this result is called time dilation. So this is the next paragraph, the meaning of time dilation. Now in these pictures, these two pictures, I have clock here, clock there. So it may be just ordinary clock. It may be your watch. It may be your pulse. Because pulse, you have pulse, tick, 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 tick. That is like a clock. So your pulse may be considered as a clock. So clock is a very general term. Here, the word clock is any clock. Whether it is a watch, it can be a watch, no? It can be an ordinary clock. It can be a bouncing spring. The spring bounces up and down, up and down. It is like a clock. A pendulum. A pendulum swings left, right, left, right. It is like a clock. A beating heart. I just mentioned it's your pulse. The pulse is like a clock. It beats. Tick, 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 tick. So it is a clock. A dividing cell, if you study biology, a dividing cell has a certain definite time, it's a clock, or galactic event. That is something to do with astronomy. Anyway, anything which occurs regularly is a clock. So from the equation, we learned that the time is relative. Relative to what? Relative to observer. If the observer is different, different observers may have different time measurement. So there is no absolute time. That is the topic of the time dilation. It's from theory of relativity. So the next page, let's further look at the equation. The equation has a square root, this quantity. The equation has a square root of this quantity. You know that the inside of a square root cannot be negative. A negative doesn't make sense. So this quantity must be positive. So let's do the inequality. This is positive, which means this is less than 1. And this is less than 1 means V is less than C. V square is less than C square. If V square is less than C square, then that means V is less than C. So this is a result from the equation that the inside of the square root must be positive. So the conclusion is that the velocity of your train, of whatever, the velocity of your car, and so on, anything which moves cannot be equal to the speed of light. It can only be less than the speed of light. Therefore, anything moves has a limit, the speed limit here. Anything moves has a speed limit. The speed limit is that the speed is equal to or greater than light. This is not possible. No material object can have a speed that is equal to or greater than that of light. And that is the result from the time dilation. And this is proposed by Einstein. And nothing can move faster than light. That is the result. These two paragraphs just tell you that the time dilation from the equation is proved experimentally in 1971 and also in 1976. These two experiments prove that the theory of time dilation is correct. We are not going to mention any details of these experiments. Okay. But this is an interesting result. When something moves, let's go back to our diagram. When this moves, the clock reading here is different from this person who is not moving. The clock reading that. This reading is more than this reading. When you move, your reading is smaller compared with someone who is not moving. So if you are moving, if you are in a spaceship, so you move very fast, then when you spend, say, 10 years in the spaceship, your friend on Earth has spent more than 10 years. So your time is smaller than his time. So I'm not going to explain this in detail, There is a name for this result, which is called as a twin paradox. We will discuss this next in some other time. So let's go to an example. An astronaut whose pulse frequency remains constant at 72 beats per minute is sent on a voyage. So he may be in a spaceship. What would her pulse rate be relative to Earth, relative to a person on Earth, when the ship is moving relative to Earth at this speed and at this speed? We must understand pulse rate means pulse frequency. And what is period? Pulse period. Period is 1 over frequency. Therefore, pulse frequency is 1 over pulse frequency. So 1 divided by 72 is this many minutes. Period has a unit of time. And remember, this is a time when this person is not in a spaceship. It's at rest. Therefore, this is delta Ts. All right? Delta Ts. When it moves, when this astronaut moves, then the time is delta Tm. So delta Tm is this. So you have the formula. And just do the substitution. Substitute this time into here. And substitute velocity. For part A is 0.1 c. Put it here. You do the calculation. You get this. This is the pulse period. And what is the pulse frequency? It's just 1 over. So let us do 1 over. So the pulse frequency is just 1 over the relation on the previous page. And you get, this is a pulse per minute. That's a pulse rate, 71. Sorry. We started with 72. So 71 and 72 is not much difference. So at this speed, 1/10 of the speed of light, the pulse frequency is almost the same as before. Now part B, the speed is much greater. It's 90% of the speed of light. You put everything into the formula, and you get this as a period, pulse period. And let's find the pulse frequency. It's 1 over this number, and just do that, and you get 31 pulses. So you see the frequency changes very much when the speed is great. It was 72 before, but now at 90% of speed of light, the frequency becomes 31. It's much less. It's much less. Because the speed is so great, it's 90% of the speed of light. So this is the example, and the following is the practice. I have 3 practice questions, and I have explained the most important thing is to identify which time is Tm and which time is Ts. That's the most important. I helped you by putting a bracket. This time is Tm and the other time is Ts, and so on and so forth. And I have given you the answer part. Okay. Try your best to do these 3 practice questions. If you have any questions, we can communicate by using this telephone number. So this is my information if you want get in contact with me. Okay, so copy this number down, and if you like to join the class, you will get my notes, and you get exercises, and you will get the exercise back. I will correct your work, and I will give comments why your work is not correct and how do it correctly. And I can also talk to you in real time. If you call me by the telephone number, I can talk back and tell you the detail. Or we can use email or use whatever method to communicate. And if the class resumes after the pandemic, after COVID-19, we can have class, face-to-face class. And in that case, we can discuss much better that way. Goodbye. Thank you for watching. See you next time.